Our first submodule will be a review of basic terminology for equations and inequalities. So we'll discuss lower order polynomials like linear polynomials and quadratic polynomials, and also exponential, logarithmic, and absolute value functions. So let's just remind ourselves what these look like. So when I say a polynomial, I mean powers of x, and we will focus on the first order case, or linear polynomials. Okay, so these look like ax plus b equals 0 for some constants a and b. And then we'll also talk about, and actually more at length, about second order polynomials, also called quadratic. Okay, and then there's an important formula for this that we'll go over called the quadratic formula, or QF for short. Okay. We'll then move on to exponential and logarithmic formulas. So these look like y equals a to the x for some constant a. So for example, y equals 2 to the x. Okay, so things like, if x equals 1, we would get 2. If x was equal to 2, we would get 4. If x was equal to 3, we would get 8. So these are functions that have kind of this doubling property, or this sort of geometric growth, where at each new variable I'm sort of multiplying by a number. And then we'll look at its inverse function, logarithm. Okay, and this, if you're not familiar, this is essentially defined to be the inverse of an exponential function, in the sense that if y is equal to log base a of x, that's how you read this. This is the same as saying that if I take the number a and raise it to the y power, this is equal to x. Okay, so in some sense, the logarithm is giving us a way of solving exponential equations. And in fact, they are what we will call inverse functions. And then the last thing that we will look at is what's called the absolute value function. And this is actually rather straightforward. This just says if I have a positive number, don't do anything to it. If I have a negative number, kill the negative sign. So it turns negatives to positives. Right? So one way to write this is that it's equal to, let's say, a if a is greater than 0, and negative a if a is less than or equal to 0. Okay, so it's a way of saying take whatever your input is, keep it the same if it's positive, and make it negative if it's negative to start. So just drops any negative signs that you have. Okay, so the way that we typically solve equations and inequalities involving any of these types of functions is to do algebraic manipulations. Okay, so things like adding something to both sides, exponentiating both sides, taking square roots, these are all algebraic operations. So we manipulate with these in order to solve our equations. One of the key differences between equations and inequalities is what the solutions will look like. Right? So equations have the property that, in most cases, their solutions are discrete points. Okay, so that is to say, some sort of finite collection of points. Whereas inequalities typically have solutions for, of many, many points, infinitely many points. Okay, so these might be thought of as regions for solutions. Okay, so just sort of as a small example, if I have the equation, let's say f of x equals x, and I want to know when, let's say, x is less than or equal to 0, or let's say x plus 1. And I want to know when f of x is less than or equal to 0. Well, how would I solve this? Well, I would say f of x is equal to x plus 1, less than or equal to 0, and then I solve for x. So x should be less than or equal to minus 1. So any number less than or equal to minus 1 will be a solution to this. So for example, -2, -3, -1000, these are all solutions. So there's infinitely many solutions to this inequality. In comparison, if I asked, when does f of x equal 0? Well, I'm solving it in a similar way. I would say this is the same as saying, when does x plus 1 equal 0? That is, when is x equal to minus 1? So here I have one solution, not infinitely many. But in many ways, our procedure for solving these was the same. But it's important to understand how the solutions are somehow structurally different. Inequalities typically have many solutions. Equalities or equations typically have fewer. Okay, and then there are certain important rules that we can use sometimes to solve equations. One that we will emphasize is what's called the quadratic formula. So let's take a look at that. So one of the sort of most classic examples in studying polynomials is the case of how to solve second-order polynomials. So things that look like some constant times x squared plus some constant times x plus some other constant. And the killer term here is this x squared term. It makes things kind of nonlinear and complicated. So if I just gave you this equation and said try and find solutions to it, I think it would be difficult. But there is sort of this beautiful and standard formula called the quadratic formula that says if I want to solve an equation for a quadratic, all I need to do is plug its coefficients into this formula. That is, I need to plug the a, b, and c in, and then I will be able to get the solutions rather quickly. So the quadratic formula is stated here. Okay. So I take the coefficient on x, take minus that, that's this minus b piece here, and then I say take plus or minus square root of b squared minus 4ac, and then I divide the whole thing by 2 times the coefficient on x squared. So it's worth noting that we actually have two solutions in general to this quadratic coming from the plus and minus here. This gives us a solution corresponding to the plus and a solution corresponding to the minus. So in almost all cases, we get two solutions, not one. There is a sort of one case in which we only get one solution, and it's when this b squared minus 4ac is equal to 0. In that case, in the quadratic formula, we're adding and subtracting 0, so it doesn't do anything. This is called the discriminant. So named because it lets us discriminate between the cases in which we have two solutions, which is normal for this, and the sort of exceptional case where we only have one. Okay, so let's look at a few examples of applying the quadratic formula. So here's a very typical problem. It's x squared minus 7x plus 9 equal to 0. So I have this is second order or quadratic because I have an x squared term here. So to solve this, something we can do is use the quadratic formula. So in this case, it might be helpful to write down what a, b, and c are. So remember, a is the coefficient on the x squared term, so a is equal to 1. B is the coefficient on the x term, so minus 7. And c is the constant, so 9. So once I've written these down, I just run it in the quadratic formula. So x equals negative b, so negative 7, plus or minus square root of b squared, so minus 7 squared, minus 4 times a, which is 1, times 9, divided by 2 times a, which is 1. So all I have to do now is evaluate all of these little pieces. So negative 7 is 7. What is the square root of minus 7 squared? 49. And then minus 4 times 9 times 1 is 36. Divided by 2. I think this is 7. So I just get this. Okay. So in this case, trying to make it simpler is difficult because square root 7 does not simplify. Another way of saying this is 7 is not a perfect So we cannot simplify this any further. This is sort of as compact as the solution gets. Okay, so notice that we get two solutions, 7 plus square root 7 over 2 and 7 minus square root 7 over 2.